All right, line V1 used to be learning task 8, so it's now going to be learning task 1 here from my motor controllers, but what we're looking at is DC motor control features. And we're going to go through the main features of them, which are going to be really just to start, stop, and reverse, so to cause operation of my DC motors, to control the motor starting current and torque. If I control the amount of current, I'm going to be able to go and control the torque that I'm going to have out of it, and to go and provide the correct operating sequence and speed control of any sort of driven mechanical system. And this is the 3 main purposes of any motor starter, whether it's going to be for AC or DC. Let's start by talking about manual starters. All that a manual starter does is it starts and allows the motor to accelerate. It says in your book that it starts and accelerates it. It's the actual motor itself that is going to go and cause that acceleration. They are going to require human operation of a switching device to control the energy that we're going to go and send out to it. And they are going to have to be a heavy-duty type of system that they are going to have. We're going to go and have DC-rated systems that we're going to have to go and look at. And the reason for a DC rating is all to do with our different types of current. DC can look like a number of different things. DC can look like this, where it's going to go and be pulsating DC. DC can also go and look like this, where it is going to go and be a continuous high value of DC, rather than this pulsating one. This one would be a rectified. This other one down here is going to go and be a rectified and filtered and basically trimmed type of DC, where I'm going to go and have a unified DC. And this is much more common inside of heavy industrial systems, where they're going to go and have a DC bus that is non-pulsating. Because as soon as you have non-pulsating DC, you eliminate a lot of your losses that are going to be inside of the system, and more shred losses, etc. So we are going to go and have DC rated contacts inside here, and the reason for the DC rated contacts is because I don't know which one of these 2 systems I'm going to be looking at. I have to assume the worst, and the worst case type of system to go and switch would be this one over here, where I have got a unified amount of DC. Think about it this way: when I close in a set of contacts, we'll just draw a set of contacts right over here and right over here. When I go and literally close these 2 in, I'm going to go and have current that is going to go and make connection across. So we're going to go and flow current through there. That's all going to be fine. It's not going to be so much on the closing in that we're going to go and see the issue here. I'll just draw the face is closed in now. It's going to be when I go and try to open this, because when I try to go and open this, what I need to do is I need to go and break that current. Over here, what I see on this unified or this level DC that I have is that I'm going to have continuous value of voltage and continuous value of current, which means that as I draw these 2 apart, there's going to go and be arcing. That's going to go and happen between these 2 contact points, because my current never drops away. This over here, my rectified types of DC or AC as well, cross through my 0 axis or get down to a value of 0 volts 120 times a second, right? 60 hertz, and it goes through once on the upswing, once on the downswing. So 120 times a second, we hit this 0 volt, which means that my arc for a split second is going to go and extinguish, and then it's going to have a harder time trying to go and reestablish. And it's going to extinguish, and then it's going to have a harder time trying to reestablish, etc. Which means that AC rated contacts are able to be much smaller than what I would need to go and have for a DC rated. DC are going to go and have a much, much greater rating that is going to be required. They need to go and have bigger contact faces. They need to have faster operation, just due to the way that they switch out this type of DC current. For small DC motors, often what I'm going to do is I'm going to go and stick in a SPDT switch. You should know these short forms over here. This SPDT would be single pole, I said the wrong one over here. Double pole, DPDT, double pole, double throw switch that I'm going to go and switch out both lines with. And it's just going to be a switch where I have both of these contacts that are going to be connected together. DPST. Man, I just can't get it right this morning here. Double pole, single throw. We throw it once to close it. We throw it back to go and open this thing up. Would be the switch that I would need for a small DC motor. You can go and downstream of that, inside of these switches, you can go and incorporate overload devices. Those overload devices are simply going to go and be heaters that are then going to go and send out a trip signal that's going to be able to go and trip out that switch over there. Once again, the overloads themselves do not go and open themselves. If I've got larger DC motors, I'm going to go and have a longer time that I'm going to need to accelerate. I'm going to have a massive amount of inrush current that's going to go and happen. Remember, we talked about this before, that when I start something up, I get a massive amount of inrush, and then it's going to go and taper down to my operating value of current. So we're going to go and have different types of controllers that are going to go and give us that slower rate of acceleration. All right, let's talk about the thing that's in the picture over here. What we're showing inside the picture here is a drum controller, and a drum controller is a handy little switch that we can utilize for both AC as well as we can utilize for DC components of any sort of a motor. Let me just delete these over here. Delete that in around here. And what those drum controllers are going to go and do for us is they're going to have a switching arrangement, so I can feed this thing AC or DC. It's rated for a larger amount of AC than what it is for DC, because the DC's got that continuous current potentially. And it's going to allow us to swing this handle in either direction. It's going to be spring loaded, so it comes back to the center. Now on this one over here, this is an AG5 series of square D drum switches over here. You can see the little square D logo over there. These ones over here, you can actually remove the spring tension. It's part of what the manufacturer allows, so that you can have them maintained, so you can push it into either position and it's going to stay there, or you can have it that it's going to be manually, where the operator has to have a hand on it at all times. We use these in a lot of cases for positioning, because what they'll allow us to do is they will allow us to go and form a couple of different sets of connection. Over here, I want you to notice that in the off, or the central position, there's no connection made between 1, 2, 3, 4, 5, or 6. When I go and switch, I see that my reversing over here is going to go and give me 1 to 2, 3 to 4, 5 to 6. And when I go forward, I'm going to go and see that, 1 to 3, 2 to 4, or 5 to 6. Really what we are looking at over here is something very similar to what we see inside of our four-way switch. Inside of our four-way switch, we commonly draw this thing out as being ... and then that it can kind of crisscross across like that as well. We're seeing the same type of action that's happening inside of here, except instead of going kitty corner across, it's just going ... high, or high, low across. 5 and 6 always just makes the same connection. Now they are going to come with a set of instructions inside them for how to hook them up for various types of different motors. But if you go and take a look at our connections that they're showing us inside here, we are utilizing all of these connections. 5 and 6 is just going to go and disconnect one of my lines. I see that on all of these, that it's going to do and disconnect one of my lines that's incoming. And then what I'm going to do is I'm going to go and use this 1, 2, 3, 4 group up here to reverse my incoming lines. Let's take a look at a shunt motor off of this. We'll start with the shunt motor. It's easy enough to go and take a look at. The first thing that I'm going to note is that I have got constant power to my shunt field on one side, this one over here, through my 5 and 6. So as soon as I go and switch this thing either into forward or into reverse, I'm going to go and make contact across here. Okay? We're going to go and say that forward is going to go and be blue. We're going to say that reverse is going to go and be a red set of contacts inside of here. Let's take a look at how this thing operates in forward first over here. In forward, I'm going to go and make a connection that is going to go from my line. It's going to allow me to send current through my armature and then back down in like that over there. If you follow that direction of forward current through here, you would see that I'm going to be able to pass current through the armature in that direction over there. If I want to go and reverse this motor, I'm then going to have to go into my reverse. And if I do reverse, I see that once again 5 and 6 is going to complete the path for my shunt field. So the shunt field is going to go and energize. But now I'm going to go and make this connection over here. And when I make that connection over there, I'm going to go and have my current passing through in the opposite direction through to my lines. We'll just go and cover that current one more time just to show how this thing operates. Once again, if I take a look at just the armature, remember we always want to go and reverse the armature. In reverse, my armature connections are this, which means that I'm going to go and have current that is going to go and travel through negative to positive, like that, and back out over there. If I were to go and place this thing into forward, these connections over here are all going to be made. And once again, taking a look at my current flow, I'm going to have current that's going to go in, up. It is going to go the opposite way through my armature now, and then back out to my line. All of these connections inside of here are going to go and do the exact same thing. They're just going to be reversing the current that I'm going to go and be driving through my armature. If I take a look at a series, I see that that series is going to always have the series field, the S2, that's going to be connected to my negative over here, no matter what it is. So I'm always going to go and get the same direction of magnetic field inside of my series field, but it's just going to be my armature that is then going to be either connected through and through, so that I'm going to be sending my current up through like that, or it is going to be connected through and through, so I'm going to be sending my current up, let through like that. Either one of these is going to be operational for my series one, and then compound motor over here. Compound motor, you'll note again that once again I have got my fields. Check this out. My fields are always stay connected to a hard line. This 5 and 6 is always just going to be switched across there, and it's just going to be reversing of my armature. That's going to happen inside here. Follow these through. Spend a little bit of time on the drawing, but you can go and follow these through with both the reverse operation and with the forward operation side of your book. And you will see that we always are going to go and have the fields are going to be the same. No matter if we're in forward or reverse, we're going to have the same direction of current through them. Armature is going to go and reverse. We're going to go and change the direction of current through our armature. And this is just standard for what we would go and do inside of a regular DC motor. We talked about this. Reversing the rotation can be done by switching either the field or the armature, never both, but the standard is always going to be switching that armature. All right, let's talk about these things over here, the 3-terminal and the 4-terminal faceplate starters. Faceplate starters are going to be used off of a larger motor, and these are going to go and provide us with acceleration control is what we are really looking to do. Acceleration that we are going to go and have. In a lot of cases, these are also going to go and be incorporated with an ammeter that is going to go and be connected to that line. We'll go and use like a shunt type of ammeter where we can go and see what the current is, because we know that once again when we start, something is going to go to a ridiculously high value current, then it's going to go and drop back off. We call this the inrush. And if my system cannot go and handle that, what I'm going to have to do is I'm going to have to go and push a lever through, click, 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 click. We'll go through these steps here in a second. And I'm going to try to maintain that proper value of current, that I'm not going to let it get too high off of here. A couple of things that I want to go and talk about on here. First thing that I want to go and highlight is this thing called the holding coil. What you'll note is that this holding coil is going to go and be in series with my shunt fields. The reason for this is that then we are going to be able to go and monitor what's happening inside my shunt field. Now, my holding coil is not going to be a very large magnetic coil. It is going to go and be in series with this so that anytime that I lose my current, if I were to go and lose my shunt field, I would therefore lose current through this coil. And if I lose current through a coil, I'm going to go and lose magnetism through a coil. It's going to allow me to go and release something. In this case, it's going to go and be this control arm that we're going to be looking at. This is just going to be a protective device that I'm going to go and have over here. The other thing that I'm going to take a look at is the fact that my armature is connected in series with a whole pile of resistances going across here. Those resistances going across there are going to allow me to go and drop, when I start out over here, lots of resistance, less. So I'm going to go and have lots of resistance initially inserted. I is equal to E over top of R. So initially I'm going to have a large amount of resistance, but then I'm going to start dropping that resistance, which is going to go and allow my current to go up through here. If I were to just throw this thing in, if I were to make connection across from here to here initially, we would have too big of an inrush on our system. We're attenuating that with this. Last thing that I want to go and talk about off of here is that once again, there is a small error inside of this thing. You should have seen this drawing before, by the way. You guys are lucky. But there should be no connection going through inside of there. Okay, there should be just a isolation going across there. We'll just draw another little dot up top there. I know it's kind of hard because it's whatever. It's getting all janky here on me again. We'll try one more time. Okay, and we'll hopefully that one is going to go in holes. Okay. That's what it should look like. There should be no connection between the resistance over to this swipe bar. And the swipe bar is just a continuous set of contacts that is going to allow me to feed current in through this contact arm all the way up and through. Last thing that we'll talk about with this before we go into the operation is the fact that this is going to go and be spring loaded. There's going to be a physical spring that is providing tension back in that direction, which means that as we push it forward, we're going to be fighting the spring. When we actually lock it in down over here, it is also going to go and lock in up against a spring over there. But if we were to lose this coil, it's going to go and pull itself open. Okay, here's how we start this thing up. We're going to go and follow our lines through. Now I've got line 1, which is connected up top over here, goes through this arm. This arm itself is going to go and be live on the inside. The handle that you grab out here is going to be insulated, so you don't have to worry about that, but I'm going to go and treat this whole thing as being live. As soon as I start to push this handle forward, the first thing it's going to make contact with is it's going to make contact with this sliding arm over here. That sliding arm is just going to go and provide us with a continuous live onto there. As soon as we push this thing forward, we should see that by me making contact with that bar, I am going to have a complete path for my current to go and flow through my shunt field circuit. Let's just take a look at this over here. If my switches were closed, I would have a complete path through this coil up to this bar, and then through this bar back out over here. Complete path that has got no extra resistance inside it, meaning that we're going to go and get full shunt field magnetization. Okay, we'll make a big green magnetic cloud right over there. We're going to get full shunt field magnetization that is going to go and happen the second that we start to make contact with this over here. That's great. So the first thing that we see happening is going to be that contact. I'm going to erase that right now because past that we don't need to go and look. It doesn't matter where this arm would be across that bar. There will always be a path now through my shunt field, causing me magnetization. The second thing that I'm going to go and take a look at is this point of contact that's going to be across here. I'm going to trace this one through with a blue line. I see that initially when I push this bar up to here, I'm going to make contact across to that first dot, which would mean that my path for current flow through my armature is now going to be through the armature, through all this resistance, down the bar, and through here. So I'm going to have a lot of resistance that's going to be in line. Because I've got a lot of resistance, I'm going to be dropping the current, but my motor is going to now have current applied to the armature, which means it is going to start to rotate. So it's going to start to rotate. As it starts to rotate, its counter EMF that it's going to go and have inside of it is going to start to go and rise, and as its counter EMF starts to rise, its amount of current is then going to go and drop inside of it. So I'm going to be monitoring my lines, and I'm going to go and see that, my current is dropping, and then I'm going to go and push it over to the next position. We'll just do that a sec. We'll move this thing, move this one over here. I'll push it over a couple of positions over here. Push it over up to here. As soon as we see that this thing has been pushed further, we once again see that we still are passing current through the armature, through resistance and out, but I'm now passing it through less resistance. But because I'm already rotating a little bit, I'm going to go and have less inrush. And so once again, as we move from step to step to step, we're going to be dropping the amount of inrush. Every time I move a further step, there's more current through the armature, which means this motor is going to go faster. We're going to go and increase our amount of torque. And with each one of these, as I move onto each step, the motor gets faster, the counter EMF goes up, the overall amount of current is going to go down. We continue doing that, pushing this thing all the way across until we reach this point over here. And when we reach this point over here, what you'll see is that we have got full current going through here. There is zero resistance in line with my armature at this point, right? No current's going to travel down there. There's no need. There's no complete path for it to go and travel the rest of the way through there. Therefore, I am not going to go and have any sort of a current traveling through, and I'm not going to have any extra drop. The only thing that is going to be in line with this right now is going to be the armature. If you were to go and trace this through right now and draw this thing with the arm pushed all the way across there, what you would see is that we would have a circuit that looks like this. There's our armature. And then we also have got our shunt field, which is going to be in line with a coil, loss of field relay. We're just going to call this the LFR, loss of field relay, that is going to be connected in there. If I were to lose that field, I would lose that relay. Now this relay is a magnetic relay. It creates a magnetic field. Stick a very small blue magnetic field around it. That magnetic field is designed to go and seal in up against that little magnet that we see over there on the contact arm. So it is going to go and hold this thing in. All we're going to do is we just kind of do this one push, tick, 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 boom, and then it's going to get held in by a magnet. Remember, there's spring tension trying to go and pull it back. If we were to go and lose the fields, we would go and lose the path of current through the relay, which means we would go and lose all of our magnetic fields, which means that that spring would be able to go and yank this thing open. Boom, we would go and yank this thing all the way back open. It's a great little system. It prevents us from having that point where we go and lose the shunt field, because inside of any shunt or inside of any shunt-heavy compound motor, we know that if we lose that shunt field, or if we increase the resistance, that we would then go into an overspeed off of that shunt. We want to try to avoid that. I think that's it for anything I want to highlight off of this one. As far as shutting this motor off, all you would need to do, by the way, is just provide a little bit of a tug backwards off of this thing. If you would go and give it just a little bit of a tug, you're going to break that magnetic contact over there. It's not a super strong magnetic contact. And then the spring action would be able to pull this thing back down through, and it'll actually give you a little bit of deceleration on the motor as well. Let's talk about making this thing go faster than its base speed, because right now what we were doing is we were just giving this thing a little bit of a push all the way through, and as we were giving this thing a push through, we were going from 0 all the way up to base speed that we were going to go and have. If we want to go higher than base speed, we are going to need to go and put in another component over here, and that other component is going to go and be a rheostat in line with my fields, my shunt field that I'm going to go and have over here. Now, this one is different than what we just saw in the 3-terminal. The 3-terminal over here gave me loss of field protection, or no field type of protection. We saw that through this little relay, which was acting as both my holding coil and my loss of field relay that I saw over there. This one over here is going to be different in that this holding coil is simply going to go and be a holding coil alone. It does not provide loss of shunt field, because if I were to go in series this thing with the rheostat, the holding coil and stuff like that, I could build my own little arrangement to do that. If I were to go and do that, anytime that I were to adjust the rheostat, increase my amount of resistance, I might drop my current below whatever I need inside of my holding coil, and then this thing is going to just drop right out, even if it was a value of speed that was safe and was actually desired off of here. We don't want to go and see that, so we are going to go and have to do a external speed sensing. The best way for us to go and do this external speed sensing is we are going to go and use a centrifugal switch, which is just going to be a switch which has got a special set of flyweights. It's going to be mounted to the motor shaft, and if it gets too fast, it's going to go and pop open a set of contacts, which we will then use to go and de-energize all of this over here. We're going to cover centrifugal switches later on once we go into AC. Right now, we're just going to go and say that there is such a thing as centrifugal switch, and that it would be incorporated somewhere upstream. We would have a set of contacts upstream that would be connected to this thing that would be tied to that centrifugal switch. So if that centrifugal switch were to go and operate, we'll just draw a little symbol for a centrifugal switch over here. It's going to be an arrow that goes between 2 points like that. If it were to go and operate, then it would go and kick out this coil and open those contacts. But we'll leave that alone because it's not necessary for what we're going to go and look at over here. Right now, we're going to go and deal with external loss. Let me just finish right this though. Loss of fields through centrifugal or mechanical type of speed switch. What we're going to deal with on this one is, once again, we're using this setup over here to accelerate a motor. That's all that we want to go and do with this one. Same deal as what we saw before. We are going to go and have this swipe bar that we are going to have over here, and we see that is I go and make contact. The first thing that makes contact is that swipe bar, which would mean that that swipe bar would be fully live at that point. And I see I've got a couple of things that are going to be tapped off of that swipe bar. First thing that I see that's going to be tapped off of that swipe bar, which is one of my first thing that's going to be live, is I'm going to go and have this current path over here, which is going to be going through my shunt field and through my shunt field rheostat, which I'm going to go and use to accelerate this motor above base speed. I'm also going to see that I'm going to go and have contact from it through my holding coil and back down to here, which means that I'm going to go and have a magnetic field that is going to go and operate on this holding coil over here as well. All right, I'm going to erase both of those because we don't need to analyze those in depth. The only thing I'm going to point out is that when I'm starting this thing out, I want the shunt fields rheostat here to be at a minimum during start, just so I can get my maximum amount of current that I'm going to be able to out through that shunt field to go and drive this motor. So we're just going to leave it like that for now. Let's go and talk about the actual starting resistance that we are going to go and place in here. This case, we are going to keep that little connection inside there. It's going to be fine for us to go and have that connection inside there. There will be a little bit of current that might travel through here, but it's not going to be a lot of current that is going to go and travel through here because current's going to take a path of least resistance. We'll sketch those out as we go along here. Same deal as before, my arm, the actual contact arm, is going to go and get moved across to differing positions. As I move across to differing positions, we are going to see a path for current that is going to go through my armature. Let's take a look at this path over here right now. I see I'm going through the armature, through a value of resistance, and then it goes down through that arm and back out. So I would see that as I'm pushing it across, there's resistance in line with the armature, once again, just to limit the amount of inrush current that I would go and have. If I take a look at these resistances over here, these resistances are still attached across to here. Will I get current flow through here? Hardly. There will be some electrons because it is a parallel path still, but it's going back to the same point over here on the arm, which is going to go and be seen as being a positive at that point. That positive point, we have to be very careful about that. We don't just assume there's not going to be anything going through there, but we understand that it's a very high resistance that is going to be in parallel with a very low resistance. If I were to take a look at these 2 points over here, basically that's what we're looking at. We know that when we've got two resistances in parallel, the overall resistance is always going to be lower than the lowest one. So it's not going to go and give us more resistance in there, but there will be a tiny, tiny amount of current that will travel through it compared to a much, much larger amount of current that's going to be going through the actual contactor. So let's not worry about that little constant path that we have inside of there. Let's take a look at our main path for current that we would get when we push this bar all the way over. I'm just going to draw that one out. Just get rid of that little one there as well. If I push this bar all the way over to here, I would see that I'm going to go and have my main path of current that's going to go through the armature, through this contact bar, and down and back out onto my line over here. When I do have that path, I'm going to go and have full value of current that is going to be through my armature. And when I've got that full value of current through my armature, I'm going to be able to go and get full speed on my motor. Now at this point, once I've accelerated my motor all the way through, what I can do is I can start to go and play with this rheostat. As I play with this rheostat, I'm going to be able to go and accelerate this thing above base speed. Note once again that this holding coil is designed just to go and hold this armature in. Remember how we talked before about the fact that there is going to go and be a centrifugal switch that is going to be attached, or a mechanical overspeed switch that's going to be attached? What I'm going to do is I'm going to go and oftentimes insert whatever is going to go and be in contact with that. It's going to be a normally closed contact that's going to be associated with my centrifugal switch. I'm going to put that into this line over here, so that if this thing does get too fast, the centrifugal switch is then going to operate its mechanical normally closed contact over here, which would then drop out this holding coil. And as soon as it would drop out this holding coil, then this arm would go and pull all the way back out to the point where it goes and breaks all points of contact inside of here. This one is called the 4-terminal starter. Reason for the 3-terminal starter and the 4-terminal starter is just the number of terminals that I'm going to go and have inside there. L1, F1, and A1 on that one, which is my 3-terminal. And then on this one over here, L1, L2, and then F1, A1 that I'm going to go and have over here. Note that my A1 is actually connected to my A1, that my F1 is actually connected through my rheostat to my F1 on this one as well. All right, let's go and talk about magnetic starters or contactors. We have in previous years dealt with motor control and motor control contactors, which are just going to be a way that we can use a small amount of current to go and create a large magnetic field that's going to go and pull in a set of contacts. This is a DC magnetic contactor, and it's going to be a single pole magnetic contactor. In DC, sometimes we only actually break a single line. It's common to go and break two lines because as soon as I break two lines, I split my arc in two places and it allows me to extinguish an arc. But in some cases, you will see these single ones that we are going to go and have over here. What we will have inside of here is a number of different components. It's a rough drawing, but it shows you we're going to have an electromagnetic housing over here. We're going to go and have an armature that is going to go and get attracted towards the electromagnet when we go and provide power to the electromagnet, the coil. And then we've got a spring that is always serving to try and pull this armature back out. The magnetic field is going to be able to overcome the spring, pull that thing in during operation, but if I were to lose my magnetic field, then the spring is going to go and retract this, pull this back out. We've got a number of points for us to go and make contact. This is not a physical handle. This is just going to be where I'm going to have one of my contact points over here. Over here, you see that there's a big flexible braided copper lead. We are going to go and have our other terminal, which is going to be back down over here. And basically, we're going to go and have a line in and a line out off of these things. This is going to be your line in because it's going to be shielded. This over here should be your line out because it's going to be the bare one, so we could shut this thing down. And then we are going to go and have a set of smaller contacts over here that we're going to go and utilize for a coil. Now, this is only one of many, many variations that we have. We've got ones that look like our regular contactors. We've got ones that are these, single pole type of contactors, etc. All of them are going to go and have a couple things in common, though. That's going to be the electromagnet. They're going to have a movable part of the switch that's going to be our armature that the magnet is going to go and attract. And then we're going to have some contacts. Now, we're going to have main current carrying contacts, and we are going to go and have some small auxiliary contacts, which are just used so I can go and take a signal off of it, because in a lot of cases, my motor voltage is going to be different than my control voltage. We are going to go and have that spring assembly that's going to pull that thing back, and in some cases we are going to go and have a magnetic blowout coil. And a magnetic blowout coil is this really cool thing we would see happening inside of here. This is going to be shielded because this is going to be something that's going to be called a arc chute inside of here. And the arc chute is literally going to be composed of small fins inside of there. I'm just going to draw them for a second, that are going to go and be getting larger as we pull them further out. They're going to be more or less, I'm just going to try and put these into a straight line over here. They're going to be more or less inside of the same path. And what happens is when my contact closes, we're going to go and make a fixed contact right down over here. Okay, we'll say that thing is fixed down, and I'm going to have my movable contact, which is going to start up over here. That movable contact, when it goes down, is going to go tick, 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 tick. It's going to make contact. It's actually going to brush by each of these. Not a lot of contact, but they're going to be insulated individual ones inside of that contact over there. But they're going to be pushing this thing down, or sorry, they're going to be making contact as this thing closes in. They don't do much when I'm closing in. It's later on when I am pulling this out that they're going to go and do stuff. They're going to go and take that arc. Now, we know that current takes the path of least resistance. And so current wants to travel along each of these little metal bars. In some cases, they're actually going to go and place small little bars, that on the end just to go and pick up. They're going to be the little points of pickup so that we brush past these. And what we'll often have, often what we will have, is we are going to go and have our coil. This over here is going to be attached to an actual coil that's going to be in line with that. Right next to this over here. Remember how current creates a magnetic field. Those magnetic fields tend to go and repel each other, right? If we got the same types of magnetism, norths repel north, souths repel south, opposites attract, the sames are going to go and repel when we're dealing with all of these. What we will see is that this is going to be creating a magnetic field that is going to go and repel my arc. My arc is what we call ionized air. Ionized air is air that's broken down, has become a conductor. So I've got, as this thing opens up, I'm going to go and have an arc that is going to be established across here. What happens is this magnetic field is going to go and push that arc further out. As it pushes that arc further out inside of here, the arc, because these bars get further and further away, is going to go and get longer. And as that arc gets longer, it is going to go and have more resistance from the air, which means that it's going to go and break apart much sooner. The other really cool thing about this is that arcing immediately jumps over to these plates. It doesn't stay on my main faces where it would go and cause pitting and carbon buildup, which is going to be a form of resistance and a bunch of other stuff like that. It's a really handy little thing that is going to just allow us to break down that arc and push it out the side. You'll see it inside of some breakers, actually. If you ever work with older Federal Pioneer type of stuff, that older Federal Pioneer is going to go and have a set of small slots. You can see on the back side, that is going to be a blowout coil utilized with that equipment. Depending upon the size of the load that you are going to be putting in, you're going to have heavier contacts, right? Obviously, if I've got a high horsepower, just say I've got a big horsepower, I'm going to go and have a high amount of current. If I've got a high amount of current, I'm going to go and have beefy, large sets of contacts that are going to be used here. They're going to be mechanically large. It's going to take a fair bit of mechanical force to go and pull those things in. We're going to go and have the spring that is designed to pull these things out. It's designed to pull them out really, really, really quickly. So it's going to be a fairly powerful spring. In a lot of cases, we're going to go and have dual coils. We're going to have one that is going to go and get energized when we're pulling this thing in, and then it is going to go and get dropped out once we actually pull this thing in. So when we provide power to the coil, we are going to go and have two coils that are going to both get energized at the same time. Let's just go and draw this out as being two coils, two magnetic coils. We'll say that this over here is going to be my negative. We're going to go and say that this is going to be my contact, and then this one over here is going to go and have a normally closed contact in line with it. And so this is my A1 of my coil, and this is going to be my A2 of my coil. Unfortunately, coils, because they're armatures, are going to go and have the same as our DC motors, so we will see A1s and A2s on coils. We'll get past it. You'll be fine. You should be able to identify that this is not a motor. It doesn't look like it does any sort of rotating sort of thing. Therefore, the A1, A2 off of this is a contactor coil. What we have, though, is that when we pull this thing in, this is going to go and get operated once it gets pushed all the way in. So when I provide power to this, to my coils, both of my coils are going to go and energize. Boom, I'm going to go and have this armature, which is going to go and drive in. As the armature drives in, it is then going to go and open up that coil over there, and then we are only going to be maintaining current through the smaller coil, which is going to go and keep us, held in off of this, or sealed in type of one. Okay, the very last thing that we're going to talk about is going to go and be solid-state starters. Because we used to have a harder time doing speed control before VFDs became widely prevalent, we used a lot more DC motors. And then in DC, we would often go and have a DC that would be generated from my source, from an AC source. We would rectify a DC, which meant we had this pulsating type of DC. We're seeing that over here, where my AC supply is coming in. I'm going to go and have this bridge. It's a DB, stands on here for diode bridge, that I'm going to go and have over here. That's going to go and give me a pulsating value of DC out. And then I'm going to be able to take that DC, and I'm going to use that to do a couple of things. I see that my DC is going to go and give me permanent magnetization across the field. I go through this one way more in depth in your A6 or electronics. Go back to your week number 5 if you need to, and take a look at the video again on the DC speed controller. But I'm going to have constant power that is going to be placed through here, so I've got a constant magnetic field, and then I'm going to go and have all the rest of this, which is going to go and adjust my speed of my motor that I'm going to go and have. It's going to allow me to adjust the speed of the motor by adjusting whatever I allow to go and trigger. We've got this diac, which is going to be triggered off of this RC circuit. And my point of control on the actual main motor itself is going to be this rheostat over here. I've got one rheostat in line just so I can't get to too low of a value of resistance. I'm going to have this one that I'm going to use to adjust. As I adjust this, it's going to adjust when my diac is going to fire. When my diac fires, it's going to adjust when my SCR is going to go and fire. And when my SCR fires, it's going to adjust the amount of current that is going to go and be driven through my armature. If I fire the SCR early, so small firing angle, large conduction angle, then I would go and conduct a large amount of my waveform through, right? We can see that we're going to adjust, send a large amount through, which is going to go and give me a fairly large amount of power that I'm going to go and have out on that motor. If I were to go and fire that late, just pull out my whole main waveform, that's okay. If I were to go and fire that late, I would see nothing, 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 boom, then I'm going to go and get this small amount, nothing, 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 boom, then I'm going to get a small amount, nothing, 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 boom, I'm going to get a small amount. And we see that the amount of power that we would be able to go and drive out of this would be much, much lower. This type of operation that we have is only going to work with this rectified type of DC, because how does this SCR operate? Well, this SCR operates off of IH, which you should recognize as being a holding current. The holding current has to drop away to 0 for the SCR to go and shut off, and that happens when we have got that pulsating type of DC that's coming in. I could not, I repeat, I could not use this on a DC where I'm going to go and have a DC voltage that is going to be rectified, filtered, and straight out. So anything where I'm not using that off the AC would not work, because this SCR would at that point be impossible to go and shut off. I would have to go to a different type of solid state controller. I'm just going to sketch over this one here. We're just going to white out a whole pile of stuff over here. We'll leave that bridge rectifier inside there. We will white out this section over here as well, and we will just say that my DC is going to go and get controlled with, oh, wait for it, you guys are going to love it, this device over here, which is going to go and be a FET that I'm going to go and have. Come on. We'll go with an N-channel FET that I'm going to go and have over here. That FET is just going to go and vary the amount of DC that I'm going to go and apply through. What it would do is, where I adjust my FET is going to vary the amount of DC. I'm applying this amount of DC volts. We'll say that the top part, let's say that this is the positive over here, would be what I'm going to go and see across my armature. The bottom part would be the volts that I would drop across my FET. And by me adjusting this triggering circuit over here, actually we wouldn't be using this triggering circuit either, because this one is based off of, once again, we have to go and have that pulsing. We'll just delete that whole thing. I won't even bother drawing the whole triggering circuit, because we would have to go and get into a DC and then to a DC one that would go and collapse. We'll just erase all of that inside of there. And we'll just say that if I wanted to do it anyway, otherwise I would have to have a more complex triggering circuit, and I would have to go and use a FET that would be tied off of that triggering circuit. We'll just say T for trigger over here. That is then going to go and choose how much DC we're going to put through, and really these two get treated as being series voltage drops from one to the other. This would mean that my FET would be dropping a fairly large amount of voltage, as well as it would be carrying a large amount of current, armature current through it. So you're going to have to go and have that thing seated onto a fairly large heat sink so that you can go and get all of that heat, you can pull it off and dissipate it out to the surrounding air, right? We've talked about this before in electronics, how important that is. Okay, that is it for our features of controllers. We're going to start talking a little bit about, the operation of some of these controllers here in a minute. We did start talking about operation as far as our 3 and our 4 terminals were concerned. We're not going to go through that one again. So if you are starting to look for, how do I control different aspects on the 3 and 4 terminal, you're going to have to refer back to this features one. Cool. That's it.